The main objective of this lab was to measure spherical aberration and explore the relationship between shape factors and spherical aberration. These concepts are fundamental in optical sciences and engineering, and mastering them is crucial for designing and evaluating high-precision optical instruments.
Aberrations in optical systems arise when light rays deviate from ideal behavior, leading to image imperfections. They occur due to the fundamental limitations of lens shape, material properties, and misalignments. Aberration theory classifies these deviations into monochromatic and chromatic types. Monochromatic aberrations described by Seidel theory include spherical aberration, coma, astigmatism, field curvature, and distortion, each affecting image quality in different ways. Tilt and defocus are two common aberration types due to misalignment. Tilt introduces a linear phase shift across the wavefront, leading to a displacement of the image plane. When there is tilt in the system, the entire image shifts. Defocus results from an image plane shift relative to the focal plane, affecting the image sharpness without distorting the shape. The image becomes more uniformly blurred in all directions. Spherical aberration occurs when rays passing through different parts of a lens focus at different points along the optical axis. This happens because the focal length depends on the ray height, because rays at different distances from the optical axis converge at different points. The result is a blurred image rather than a sharp focal point. There are two types of spherical aberration. Transverse spherical aberration is the lateral deviation of a ray from the ideal focal point, and longitudinal spherical aberration is the range of focal points along the optical axis due to varying convergence of rays. Defocus affects spherical aberration by shifting the image plane forward or backward. When spherical aberration is present, the best focal plane is often defined as the point where the blur is minimized, rather than the nominal Gaussian focus.
We began by assembling our setup in an L shape so we could adjust the position of the mirror and optical components independently. Adjusting the mirror angle was crucial at this stage to ensure the beam was aligned and centered with the second rail. Once we confirmed proper alignment through the pinhole reference, we marked the beam location on a sticky note and pasted it on the wall. The assistant's alignment was extremely important, especially in this lab, to gather accurate data relative to spherical aberration. With the beam aligned, we introduced our test lens, a plano-convex lens with a 100mm focal length. We oriented the lens so the convex side faced the beam and the plano side faced the wall where our reference sticky note was placed. Next, we positioned the Hartmann mask in front of the test lens. This mask is a simple tool used to analyze ray aberrations by sampling different portions of the beam passing through the lens. It has evenly spaced holes, allowing us to control how the laser beam interacts with the lens. By allowing individual rays to be traced from different regions of the lens, we can analyze spherical aberration. Once everything was aligned, we introduced a microscope to examine the beam after passing through the lens. The microscope was mounted on a 2-axis translation stage for fine adjustments. We chose an objective lens with the largest numerical aperture available to us of 0.4 to ensure we would capture as much of the laser beam through the microscope as possible. To align the microscope, we placed a reference screen closer so that we could see the virtual crosshairs more clearly. We precisely translated, tipped, and tilted the microscope to ensure that the projected spot was centered on the virtual crosshairs of the microscope when observed.
To begin collecting data, we started from the extreme hole on the Hartmann mask, which corresponds to the marginal focus, where the outermost rays of the lens converge, by shifting the beam using the mirror translation. The on-axis ray fan was measured by scanning the mirror through each hole, while laterally adjusting the microscope to recenter the projected spot. The positions of the mirror holes and microscope were recorded, which then allowed us to generate a transverse ray plot. To find the paraxial focus, which corresponds to the point where central rays of the lens converge, the beam is again scanned through each hole, but this time the microscope is translated along the rail to maintain alignment with the projected spot. The displacement from marginal to paraxial focus is recorded, providing a measure of defocus and longitudinal aberration, which arises because marginal and paraxial rays do not focus at the same plane due to spherical aberration. The effects of lens shape factors were then tested by repeating measurements with different lens configurations. The shape factor of a lens describes the curvature distribution between its two surfaces. It determines how light rays refract through the lens. Each lens orientation impacts the amount of spherical aberration present. The plano-convex lens has a shape factor of plus or minus 1. When oriented with the convex side facing the incoming beam, b equals 1, this shape minimizes spherical aberration because it reduces the deviation between paraxial and marginal rays. However, flipping it with the plano side first worsens spherical aberration. A biconvex lens has a shape factor of 0 and balances ray refraction, reducing spherical aberration.
Our experimental results indicate that the system exhibited wavefront tilt, meaning the phase front was not perpendicular to the optical axis. This wavefront tilt leads to beam pointing errors and introduces additional aberrations in the final image. The tilt could have been caused by a misalignment or tilt error in one of the optical components, resulting in deviations from our theoretical expectations for the transverse plot, which are based on a symmetrical cubic function. When analyzing the longitudinal ray fan plots, we can infer that the shape of the curve indicates a non-ideal focus, meaning the rays do not converge perfectly at a single focal point. The presence of a turning point in a curve suggests the influence of higher order aberrations affecting the focus. Furthermore, the longitudinal spherical aberration plot for the shape vector b equals -1 exhibits a greater spread along the pupil axis, indicating a higher degree of spherical aberration, which correlates with our theoretical results.
We ran out of time to complete the experiment using a lens with a shape factor of 0, but based on our pre-lab results, we would have expected to see a different spherical aberration behavior compared to the plano-convex lens. Since a biconvex lens distributes refraction more symmetrically across both surfaces, it generally reduces spherical aberration if the object is positioned near the lens's focal point. Compared to a plano-convex lens with optimal orientation, the biconvex lens may show slightly higher spherical aberration if not used at the best conjugate ratio. However, it should still have less spherical aberration than the plano-convex lens in the worst orientation, b equals -1, because refraction is more balanced across both surfaces.